Hello. In lectures 21A, 21B, 22A, we did a lot of examples of computing eigenvalues and eigenvectors and then solutions for both differential equations and difference equations. The majority of lecture 22B involves a lot of definitions, theorems, and remarks related to eigenvalues and eigenvectors. It will represent practically everything you might want to know about eigenvalues and eigenvectors in terms of definitions, theorems, and remarks. At the very end, we'll also use these ideas. We'll talk about a discrete linear difference equation that is generated by a time one map, a time one flow map, and the matrix exponential for a linear system of differential equations from lecture 22A. All right, so jumping ahead to the linear algebra content now. Lots of definitions, theorems, and remarks, but these are all really super important, okay? And you want to get these into your soul deeply when you're using this stuff. We're not going to take the time to prove these things, but I will sometimes give intuitive explanations, and those intuitive explanations are typically good enough for most people, but it still is worth trying to remember these things. All right, definition. Let A be a square n by n matrix. An eigenvalue of A is a number that we typically, traditionally call lambda, with the property that there is a non-zero vector x in Rn. Emphasis on the word non-zero. Gotta be non-zero. With the property that, as we've seen, A times x equals lambda times x. Make sure it's really clear in your mind what's going on here. X is a vector. A times x is therefore a vector. Over here, x is a vector, the same vector. Lambda times x, lambda is a scalar times x, is another vector. A is a matrix, lambda is a scalar, a number. This equation does not mean A equals lambda. It can't. A is a 2 by 2 or higher matrix here. Lambda is a number. They are related to each other, though. You want to think about it geometrically as well. In other words, A times x is a scalar multiple of x, with the scalar being the number lambda. Visually, if you draw x as an arrow with its tail at the origin, say, and if that is an eigenvector for A, for some eigenvalue lambda, then A times x will be a scalar multiple of x. It'll be parallel to it, either in the same direction when lambda is positive, or the opposite direction when lambda is negative. Lambda itself can be 0. A times x could give you the 0 vector, that vector x getting mapped to the 0 vector. That can happen. Lambda can be the number 0, but x cannot be the vector 0. Okay? Because if it were the 0 vector, A times 0 is 0, and any lambda times 0 is 0. And so that, it's like saying the 0 vector is an eigenvector for any number, and that's too many eigenvalues, okay? We want just the same number of eigenvalues if you include something called multiplicity as the dimension of the matrix. In this situation, get this terminology right, we call the non-zero of x an eigenvector of A corresponding to the eigenvalue lambda. You could also say associated with the eigenvalue lambda. Okay? Any non-zero multiple of x will also be an eigenvector for the eigenvalue lambda. Why? Because if you take a multiple of x where k is non-zero, so that I am not looking at the 0 vector here, you can factor out the k, and if x is an eigenvector, that can be written as lambda times x, and then you can rearrange this to be lambda times k times x, showing you that k times x is an eigenvector, assuming k is not 0. These lines of equations still hold when k is 0, but we don't care about that, okay? So we want our eigenvectors to be non-zero. Equivalently, we can say that any non-zero solution x, non-trivial is equivalent to non-zero, of the homogeneous system, A times lambda I in parentheses times x equals the 0 vector. Any non-trivial solution for that is going to be an eigenvector corresponding to the eigenvalue lambda, if there are non-trivial solutions. And in fact, there will only be non-trivial solutions when lambda is an eigenvalue. Okay? Where did that equation come from? I talked about that before as well. Take the equation A times x equals lambda x. Think of lambda x as lambda times I times x. where I is the identity matrix. Subtract that from both sides to get a times x minus lambda times I times x, which is the same, equals 0, which is the same as a times x minus lambda I in parentheses times x equals 0, and then the x can be factored out. All these operations are allowed. So any non-zero solution for x that solves this will also solve this. That's the purpose of what I just did. Another definition. If lambda is an eigenvalue of A, then the solution set of this homogeneous system is called the eigenspace of A, corresponding to the eigenvalue lambda. Say that again. Lambda is an eigenvalue. The solution set, all the solutions of this non-homogeneous, of this homogeneous system, which will be non-trivial null space here for that matrix, when lambda is an eigenvalue, there will be non-trivial solutions, by definition. Note that the eigenspace of any eigenvalue will necessarily contain the zero vector, because the zero vector does solve this equation. The zero vector is in the null space of this matrix, but that doesn't mean 0 is an eigenvector. That's true in spite of the fact that the zero vector is never an eigenvector. Okay, it's still in the eigenspace by default. Eigenspaces, being null spaces of matrices, are subspaces of Rn. Okay, that's worth remarking here verbally. I didn't put it in the slides. Second page. By the invertible matrix theorem, a number lambda is an eigenvalue of the square matrix A if and only if the matrix A minus lambda I is non-invertible. Right? Because that homogeneous system has non-trivial solutions when lambda is an eigenvalue. So A minus lambda non-invertible is equivalent to lambda being an eigenvalue. Non-invertible means it's singular. The invertible matrix, part of it says a matrix is invertible if and only if the only solutions of the matrix times x equaling 0 is the trivial solution. But when lambda is an eigenvalue, we've got non-trivial solutions. There are non-zero eigenvectors when you assume lambda is an eigenvalue, by definition. Invertibility means non-singular. Non-invertible means singular. Singular is kind of a rare thing, a special thing that doesn't happen very often. In fact, when A is n by n, there will only be n values of lambda that work here, counting what are called multiplicities, which I'll talk about here soon. Also by the invertible matrix theorem, a number lambda is an eigenvalue of the square matrix A if and only if the determinant of that matrix is 0. Special, it equals 0, not something non-zero. There's only one number that's 0, everything else is non-zero. This is special, this is singular, rare. That's part of the invertible matrix theorem as well. A matrix is invertible when its determinant is non-zero. Therefore, a matrix is non-invertible when its determinant is 0. This expression here, determinant of A minus lambda I, we've seen in 2x2 cases, 2x2 examples was a quadratic polynomial in lambda. In general, if A is n by n, this is a degree n polynomial in lambda. It is called the characteristic polynomial of A. It does, in a sense, characterize A. That's why we call it the characteristic polynomial, in ways that we will see, one of which actually very shortly. The roots of the characteristic polynomial of A, in other words, the zeros of the characteristic equation, or I could call them roots as well. I call this thing a characteristic polynomial, but if I add equals 0, then it becomes a characteristic equation in lambda that you want to solve for lambda. The roots of that, the zeros of that, are the eigenvalues of A. The fundamental theorem of algebra, that sounds important. You ever learn about the fundamental theorem of algebra? You should have. First proved by Gauss in about 1800 or so. I think it was his doctoral thesis. People tried proving it before, but their proofs were incomplete. I'm not even sure Gauss's proof was the best proof, but anyway, what does it say? It says there are going to be n eigenvalues of A counting multiplicities. Why? Because what the fundamental theorem of algebra says is any polynomial of degree n, where the highest power of the variable is n, and that nth power does have a non-zero coefficient in front of it, so it truly is degree n, will have n roots, counting multiplicities. Sometimes roots, a single root, so to speak, can occur with a multiplicity higher than 1. For example, with this polynomial here, lambda minus 4 cubed times lambda plus 3 squared times lambda minus 1. That's got 3 distinct roots, 4, negative 3, 1, but 6 roots total if you count multiplicities. 4 is a root of multiplicity 3. Negative 3 is a root of multiplicity 2. 1 is a root of multiplicity 1, because it's the same as that to the first power. So you're going to have n eigenvalues of A, counting multiplicities. But there's something to be aware of here. Fundamental theorem of algebra doesn't say those n eigenvalues have to be real numbers. What if the characteristic polynomial was lambda squared plus 1? Its roots would be plus or minus I, where I is the imaginary unit, square root of negative 1. Which there's no problems with that existing. It does exist because we define it to exist. Is that a good idea to define it to exist? Yes, because it's useful. Imaginary and complex numbers are useful. Some or even all of these eigenvalues could be complex numbers, however. Something to keep in the back of your mind. Will we deal with situations with complex eigenvalues? Yes, we will. Very soon, in fact. Probably even lecture 23A and maybe 23B, too. We will deal with complex eigenvalues very soon. And that does end up implying complex eigenvectors, too. Now, you might scratch your head and wonder, how is that related to straight line solutions? And we'll talk about that very soon, lecture 23. There might not be any straight line solutions. The multiplicity of an eigenvalue is a root of the characteristic polynomial, has a name. It's sometimes called the algebraic multiplicity of the eigenvalue, which does beg a question. If there's an algebraic multiplicity to an eigenvalue, is there a geometric multiplicity too? In other words, as well? Yeah, there is. And they're not necessarily the same. The geometric multiplicity turns out to equal the dimension of the eigenspace corresponding to lambda, the eigenvalue lambda. The dimension of that eigenspace as a vector space is not necessarily the same as the algebraic multiplicity of the eigenvalue. It might be, but it might not be. And that's the thing that makes this a little extra tricky sometimes. It's nice when their geometric and algebraic multiplicities are the same, and it's especially nice when the eigenvalues are distinct, are all distinct. You've got n distinct eigenvalues. And it's also especially nice when those are all real numbers, though they could be complex. Theorem. The eigenvalues of a triangular matrix, which includes upper triangular, lower triangular, or diagonal matrices, because diagonal matrices are both upper triangular and lower triangular. Upper triangular has the non-zero entries above the main diagonal and zeros underneath. That's upper triangular. Non-zero entries above and on the main diagonal. Lower triangular has the possibly non-zero entries below the main diagonal and on the main diagonal, and zeros elsewhere. Could be zeros down here too, but these have to be zero for lower triangular. And diagonal matrices are the ones that are both upper triangular and lower triangular. So your possibly non-zero numbers are on the main diagonal, and you got zeros elsewhere. Sorry that I'm being kind of crazy with my zeros. You get the idea? Zeros elsewhere. They're on the main diagonal. Why? Think about an example. If A is, say, this upper triangular matrix, what is A minus lambda I? It would be this upper triangular matrix. And as far as the determinant of that, the characteristic polynomial, it's going to be the product of these two quantities minus the product of those two. But the product of those two is 0. It's already factored. The eigenvalues are 1 and 3. The entries on the diagonal. And it works in general for n by n triangular matrices. Another theorem, the product of all the eigenvalues of A equals the determinant of A. Huh, interesting. Product of those two eigenvalues is 1 times 3 is 3. That's the same as the determinant of A itself. And it works no matter what. It even works for non-triangular matrices. You might want to check that with some examples. I could prove this, but go ahead and check it with some examples. The product of all the eigenvalues of A is the determinant of A. You may even want to try it for a 3 by 3 example, where none of the entries are 0. See if it works. Well, if you did that, you need to use technology to help you approximate the eigenvalues in that case, most likely because you get a cubic. But then multiply your approximate eigenvalues and you should get approximately the determinant that you calculated with your technology. Another theorem. If V1 through Vk are eigenvectors corresponding to a collection of distinct eigenvalues, distinct, they have to be all different here. Lambda 1 does not equal lambda 2 or lambda 3, etc. Lambda 2 does not equal any other of these. For an n by n matrix, so I got k of these, A is n by n, k would have to be less than or equal to n. Some of these could have multiplicity greater than 1. K could equal n, then they would have multiplicity 1 if that was the case. Then the collection of those vectors is a linearly independent set in Rn. And therefore, if k equals n, the basis theorem implies the set's actually a basis of Rn. If k equals n, and these n eigenvectors correspond to n distinct, evidently real eigenvalues, well, there's nothing about that saying that they're real. Maybe they're implicitly real. I have to think about that. Okay? Let's just say these are real. If k equals n, this is going to be a basis for Rn. We can continue the invertible matrix theorem here. Suppose A is an n by n matrix. Then A is invertible if and only if. What have we seen before? It's invertible if and only if its determinant is non-zero. It's invertible, non-singular, if and only if its columns are linearly independent, if and only if its columns span Rn, if and only if its columns form a basis for Rn. Those are all equivalent to A, an n by n matrix being invertible. Since the product of all the eigenvalues equals the determinant of A is also going to be invertible if and only if 0 is not an eigenvalue of A, the number 0. Which would also mean A is not invertible if and only if 0 is an eigenvalue of A. When A is not invertible, the linear transformation corresponding to A goes from Rn to itself. If A is not invertible, that linear transformation is degenerate in some way. It's collapsing n-dimensional space into a subspace of Rn that's not equal to all of Rn. A lot of non-zero vectors get mapped to the 0 vector under that linear transformation in that case. I think just a couple more pages here. I think this is, the last page about a bunch of facts. This is a tricky page though. Something very new to most people. Take a breath. Definition. Two n by n matrices A and B are said to be similar. That's the definition. We're defining what similar matrices means, which we write as this notation: A tilde B. What is the tilde? It's not an equal sign, not even an approximate equal sign. It's just saying these are somehow similar to each other in certain ways that we will see, if there exists an invertible matrix P such that B equals P inverse times A times P. What a weird definition, but super important. Why is it super important? Because it's related to our main application of linear algebra to differential equations and difference equations, changing coordinate systems. This is related to change of basis. In fact, eigenvalues and eigenvectors are also related to change of basis. Maybe A is a non-diagonal matrix, maybe not even triangular. Maybe none of its numbers are 0. But it's maybe got distinct eigenvalues and distinct eigenvalues. I wonder if we can find a matrix P so that this product equals B, where B might be a diagonal matrix. And the corresponding system of differential equations or difference equations is completely uncoupled. I wonder if that's possible. Yes, it is possible. These are big parts of our main purpose. Okay? By the way, that equation is equivalent to saying there's an invertible matrix P so that P times B equals A times P. If you multiply both sides of this equation on the left by P, you get P times B on the left of each side is what I mean. And P times this on the right, P times P inverse, though, is the identity matrix, assuming P is invertible. And so the right simplifies to A times P, just like I have here. And I also could solve the equation for A. Multiply both sides on the right by P inverse. And I switched it around here. I can say A is P times B times P inverse. What this means actually is that if A is similar to B, then B is actually also similar to A. Because if P is invertible, P inverse is also invertible. They are inverses of each other. The inverse of P inverse is P itself. Some notes about this. Note number 2 is related to what I just said. Number 1, any square matrix is certainly similar to itself. A is similar to A. Why? Because we can take P to be the identity matrix. A would be I inverse times A times I. That would be true. I inverse is I. Second property. If A is similar to B, then B is similar to A. Essentially because of what I just did over there. Written another way, like this. If B is P inverse times A times P, then I can say A is P times B times P inverse, just like I had over there, and that could be emphasized as this way, the inverse of P inverse, which is P itself, B P inverse, that is matching this definition of A being similar to B. We're saying B is similar to A here because A is the inverse of some invertible matrix times B times that invertible matrix itself. By the way, here A and B themselves don't have to be invertible, but P does have to be invertible. And third property, if A is similar to B and B is similar to C, then we can conclude that, in fact, A is similar to C. Because these two facts, B is P inverse AP and C is Q inverse BP, where P and Q are invertible, imply that we can write C ultimately as the inverse of some invertible matrix times A times that matrix itself. Why? I'm assuming B is similar to C, so I can write this for some invertible matrix Q. I'm assuming A is similar to B, so I can write B itself like this for some invertible matrix P. And then I can use the associative property to rewrite it like this. And then it turns out that this thing does equal the inverse of P times Q. If P and Q are both invertible, then P times Q will also be invertible, and in fact its inverse will be this inverse product of two inverses. Notice the P and Q switch order. That switching of order is sometimes called the socks-shoes property for the matrix inverses. Why would it be called the socks-shoes property? I'll let you think about that. It's related to putting socks and shoes on and taking them off. I'll let you think about that. By the way, these three properties in this note here have names. And fortunately, I remember those names because they go in alphabetical order. The first property is called the reflexive property. Reflexive says that A is similar to itself. The second property is called the symmetric property. If A is similar to B, then you can, by symmetry, say, so to speak, B is similar to A. And the last property is called the transitive property. If A is similar to B and B is similar to C, it's transitive. It translates, you might say, to A being similar to C. And those names, reflexive, symmetric, and transitive, go in alphabetical order, which is very fortunate, because it helps me remember them. Similarity is not equality, but it's, pun intended, similar to equality. Reflexive, symmetric, and transitive property work for ordinary equal signs, right? Something is equal to itself, whatever that something is, if it's a number, a vector, a matrix, or maybe even something weirder. If something equals something else, then that something else equals the original something. And if, Dr. Seuss, if thing 1 equals thing 2 and thing 2 equals thing 3, then thing 1 equals thing 3. Right, Dr. Seuss? Of course, there's only a thing 1 and a thing 2 in Dr. Seuss, not a thing 3. These three properties mean that similarity of matrices is something called an equivalence relation, which essentially means it acts kind of like equality, even though it's not technically equality. And as an equivalence relation, this means we can break up the set of all n by n matrices into what are called equivalence classes. What in the world is that about? If this blob represents the set of all n by n matrices, you have to use your imagination here. So each point in this set is a matrix. We got used to this when we thought about vector spaces and function spaces and functions being thought of as points in function spaces. This similarity equivalence relation breaks up this set into actually infinitely many pieces. What's called a partition that don't overlap. And these pieces are called equivalence classes. And for any two matrices in a given equivalence class, they will be similar to each other. That's what I'm saying here. That's kind of a high-level thought. Will it be relevant for us? Yeah, I probably will bring it up again. Theorem: if two n by n matrices are similar, then they have the same characteristic polynomial and therefore also have the same eigenvalues, with the same multiplicities, in fact. Their characteristic equations are going to be the same, and they'll have the same eigenvalues. Let's see if we can figure out why. Do a quick calculation here. Say A is similar to B, and I'm thinking about the characteristic polynomial of B. Since A is similar to B, I can replace that B with P inverse AP for some invertible matrix P. But wait a minute, I can also be thought of as P inverse times I times P. Right? Yeah, that's true. And then you can factor out a P inverse on the left and a P on the right to get this. And then, hey, we have the determinant of a product of three matrices. Remember I said the determinant of a product of two matrices, A times B, is the product of their determinants. That does extend to any finite number of factors in a product. This is the same as the determinant of P inverse times the determinant of A minus lambda I times the determinant of P. But hey, this is the same as 1 over the determinant of P. By another property of determinants, those cancel, leaving you with a determinant of a minus lambda I. In other words, the characteristic polynomial of B is the same as the characteristic polynomial of A. Okay? And since the characteristic polynomials are the same, that means they have the same roots, the same eigenvalues, with the same multiplicities. Wow, that's a lot of information to take in. If you want to download this PowerPoint and have it handy to study from, especially my students, make sure you do that and rethink it through a number of times. Make sure you know all these things. Not that I'm going to ask you to list them out on a test or something, but if somebody asks you true-false questions about them, you should be able to answer those. And you should get to the point where they kind of make sense as well. Word warning, even though A and B have the same eigenvalues, they do not necessarily have the same eigenvectors. And that's related to change in coordinates. All right, our last slide here, I'm going to show you something on Mathematica. I said at the end of lecture 22A that I wanted to apply the ideas there, which included looking at sinc sources and saddle points, also at the matrix exponential and flows, the time one flow map and the corresponding difference equation. That's what I want to apply now to that example with this matrix. This is a different system of differential equations here in our linear algebra lecture B. It's good, we're mixing things together here. We saw in lecture 22A that it's got this flow where this thing right there is the matrix exponential for that matrix T times A. And this is equal to the time T flow map if I think of T as fixed. T is fixed, this is a linear transformation from R2 to itself. This is a fixed matrix times a variable vector, so to speak. Even though I've got the subscripts of 0, you want to think of those as variables. What's the time 1 map? Just plug in T equals 1. Same formula with T equal to 1. Probably would be good to approximate that. That is approximately this matrix times that vector. I should have included more decimal places. If I remember before I put this on the Google Drive, I'll do that. It's an approximation. It's a linear transformation from R2 to itself. We can try to visualize it as a mapping, which we're about to do very soon. It turns out, you might want to check this, that the eigenvalues and eigenvectors of this matrix here, this matrix exponential, this is e to the ta when t is 1, in other words, it's e to the a, are these two numbers, e to the negative 1 and e to the positive 4. The eigenvalues of this matrix were negative 1 and 4. The eigenvalues of this matrix are e to the negative 1 and e to the 4th. How about that? Everything gels beautifully. And like I mentioned, the product of the eigenvalues is the same as the determinant of the matrix. So the determinant of this matrix is e to the negative 1 times e to the 4th, which is e cubed, which is close to 20. I also forgot about the eigenvectors. The eigenvectors for these eigenvalues for this matrix are these two things, which are the same as the eigenvectors that we got for this matrix. So the eigenvalues change, but the eigenvectors stay the same. For similar matrices, the eigenvalues stay the same, but the eigenvectors change. For a matrix and its matrix exponential like this, the eigenvectors stay the same, but the corresponding eigenvalues change. Okay, it's easy to get that mixed up. The determinant is e to the negative 1 times e to the 4th, which is e cubed, which is about 20. And then thinking back to geometric interpretations of determinants, that means the time 1 map, this linear transformation here, expands areas by about a factor close to 20. Interesting. Let's illustrate that with Mathematica, and that will be the end of lecture B then. The animation I'm about to show you is similar to an animation I did back when I first started talking about flow maps and flows. Notice here in this line of code that I am using matrix X to define the flow. I got to put the T not as a superscript here, but above phi, because Mathematica thinks superscripts have to be powers, even though we know they don't have to be powers. So that enters the matrix exponential. Well, here's a static plot of the phase plane. What about an animation? Oh no, this is an animation, excuse me. So this is the phase plane for the saddle point example with something else in it. Notice there's a big black dot there at the origin for the equilibrium point at the origin, but notice there's sort of a halo around it. That's just a disk in the plane centered at the origin. Really, the origin is just one point, and really it has no area to it, even though I'm drawing it big enough to have an area. I'm just emphasizing it. But this disk here, that's kind of like a halo around the origin, is a set that's not just a point. It's a disk, a circle in the inside of the circle. And in the animation, I can look at the image of that set under the time t map as t goes from 0 to 1 by animating this. And I can stop it at any moment in time, like here's stopping it at time, this is 0.55, it says. There's the image of that original unit disk, it's a radius 0.5 by the way, under the time 0.55 map approximately. The area is not expanded by a factor of 20 because we're not yet to the time 1 map. Actually, the time 1 map makes it go off the screen. And it no longer looks like an ellipse. It actually still is an ellipse, just a very, very long and skinny ellipse. And it turns out that that ellipse, even though you can't see the whole thing, has an area about 20 times bigger than the original disk. If I re-enter this and change the radius of the starting set to be smaller, say 0.138, so you can't even see it anymore, then the time 1 map sends it to an ellipse that is like this. Again, that looks so skinny it doesn't look like an ellipse, but it really is. And its area is about 20 times bigger than the area of the original disk centered at the origin with a radius of 0.138. I also allowed myself to move the center of the disk to being somewhere else. And we can see how that set moves under the flow. Look at its images for various time t maps, t increasing from 0 to 1. And those are ellipses as well, but they don't stay centered at the origin because there wasn't centered at the origin to begin with. And if I put the starting disk, say, in this yellow region and crossing the straight line solution, we will see it gets separated, so to speak. Oops, I didn't want to change R. It gets separated into the different regions. It gets stretched out completely. But once again, the time 1 map as a linear transformation is still going to expand areas by about a factor of 20, no matter what starting set that you have. The time t map where t is less than 1, again, the area has not been expanded by 20, it's been expanded by something smaller than 20. Okay? Hope you like that. Thanks for watching.